Hello, everybody. Good evening. I hope you can hear me. Can you hear me? Good evening and hello to everybody. Welcome to our Institution of Global Professionals free webinar, which is also international and, of course, free. Thank you all for joining and stay with us till the end. Thanks for joining with us in this wonderful evening. You are a wonderful audience. I expect a lot of participation from your side, and I am your host for this evening. My name is Mrs. Rukhsana Nazir. I am from Pakistan, Islamic Republic of Pakistan, and my profession is teaching, and I'm a master trainer. I've been the principal of College of Education. I have all levels experience and 48 years of teaching experience. So, as we move on, we'll be sharing more and more because I believe that sharing is caring, and in order to succeed, we must first believe that we can. Tell yourself, I can do it, and you will do it. Energies are not released into creativity, they are bound to become poisonous and harmful. It is the ability to open our eyes and minds where limitless, wonderful discoveries are made. I have already introduced myself, but I would like to tell something more about myself. Um Starting from prep, I moved on to college, from college to as a principal of College of Education, where we trained the teachers and conducted workshops, and then to the tertiary level, I went to the university. And so I have 48 years of experience, which I want to share with everybody. I had a wonderful time during my teaching career, and I still can't stop myself from being ready to teach everywhere. Um, it is observed that many every day some new participants are coming, joining our webinars, and it is a great, very great pleasure that to have all with so much knowledge. Still, we want to share the knowledge and learn, which I think learning is a lifelong process. It does not end till death. Institute of Global Professionals serves teachers, students, and community resources, providing holistic social work and education to create a proficient generation. Institute of Global Professional, which is also known as IGP, is a leading online skill development institute with thousands of learners worldwide. For every knowledge seeker, we ensure that we make them confident, ambitious to develop their skills, provide them the best and up-to-date information to make their personalities to overcome fear and face any situation with confidence. We are recognized internationally. We try to enable our participants to show performance improvisation. Global profession is providing social work, and we believe that it's not effective to increase one's skills just by acquiring formal education. It is very true, and so we provide effective training and consultation to generate proficient generation all over the world. And teaching has changed drastically since I started teaching, and today I see vast difference. Institute of Global Professions is an educational institution. An institution provides social work with global recognition. We organize our webinar, training, offline, online courses, etc. with best and trained speakers, coaches from all over the world to create the best learning platform for all of you. Our mission is to empower people and enhance. We've already completed 349 webinars. This is the 349th one. That is, we completed 348, and this is the 349th one. And we expect that you all are getting a little bit benefited in personal and professional life, and we wish you that you all will remain with us in long journey. I benefited a lot from IGP, and here I am today as your host. And we at IGP believe to enhance your abilities by involving yourself. Let me remind you again, don't forget to share, tag, comment, and mention your friends in the comment box because your attachment encourages us to do better and best service to our lovely audience. Our mission is to empower our youth to stay with us by your support. So it is from my heart that I'm welcoming you cordially, and I'm sure you're going to learn and enjoy the webinars today. There are three speakers. I'm going to request the first speaker, but first I will introduce him to you. Our first speaker is Mr. Abhishek Wad. He's a PhD doctor, and his specialization is power electronics and drives. Abhishek Wal is interested in electronics, motor drives, and electric vehicles, and his research interest is also in these. Abhishek Paul is currently an assistant professor with the Department of Electrical and Instrumental Engineering, Thakkar Institute of Engineering and Technology, Patiala, India. He obtained B.Tech degree in electrical engineering from BIET, which Maulana Azad, Abul Kalam Azad University of Technology, formerly known as West Bengal University of Technology, West Bengal, India, in 2010, and then the M.Tech degree in power electronics and drives from Jal Jalpaiguri Government Engineering College. Excuse me if I pronounce wrong the names of the cities. Um, so he's enjoying with his research. He has several publications to his credit, and he has attended many international conferences. And rest and now request Mr. Abhishek Paul to take over and introduce himself before I forgot anything. I welcome him and all of you on behalf of IGP. Welcome again.
Good evening, ma'am. Thank you for the introduction. Uh, yeah, so right now I going to share my slides and okay.
Go ahead. Mute. Mute.
Okay, so can I start now? Okay, good evening, everyone. Today I will discuss on a very basic as well as important aspect of induction motor drive, which is used in electrical vehicles nowadays. And my discussion is based is on the how we can improve the efficiency of induction motor drive, particularly at light load operations. So, as modern culture and technology continue to develop, the deployment of induction motors has increased many times in different applications, including electric vehicles, which indeed become a promising alternative to the traditional vehicles. However, appropriate choice of any motor and associated driver system and selection of optimum control of the scheme is very essential, and these are the key challenges to address. So, mm, uh, this I will take one cases and I will explain how we can improve the efficiency of induction motor drive that are used in electric vehicles applications. And basically, induction motor drive have heavier weight and comparatively lower efficiency uh, in some operating cases, and that's why this induction motor employment in EV, that means electric vehicles, are a very challenging task. So we need to basically optimize the efficiency of such drive system before employing in electric vehicles. So the purpose of this discussion is that how we can improve the efficiency of induction motor at light load conditions. So this is the presentation outline of my discussion. This will be discussed in details in the coming slide. During the presentation, I will primarily focus on the basic concept of energy efficient control scheme, or sometimes we call efficiency optimization scheme. Then its operation, design, and real-time implementations in induction motor drive. It is to be noted that the efficiency optimization is achieved by reducing or minimizing the core loss of induction machine, and consequently the phrases like efficiency optimization, energy efficient, and loss minimization are uh, uh, simultaneously used as synonymously to present the same thing. And at the end I will show some result simulation as well as the experimental results. So coming to the introduction section, so induction motor drive is, as we know, that the induction motor is very robust and it is available in wide ranges from fractional kilowatt to mega kilowatt level, megawatt levels, and it is very reliable and cheap, as well as it is very cheap. So that's why induction motor is very popular in industry, and it is does not require any rare earth materials. So it is permanent magnet free or permanent magnetless motor, and that's why its cost is very low. So that is important aspect compared to other motors like PMSM, So that's why induction motor is used in various applications. Now, these are the application here. It is highlighted that is it used in pump or fan type of application, paper, textile, mills, different locomotives, robotics application, wind power generation. All these things nowadays induction motor is used. So, including the electric and hybrid electric vehicles or cars, induction motor now have been used. So, I have shown a data who the company that is Mahindra Electric or Mahindra, they already use induction motor in their electric cars. So these are some models they are used, that is E20 plus, E Verito, and E Suprovam. They are used three-phase induction motor, and these are the ratings. So this data I got from their website, and I have worked with a project with Mahindra Mahindra for a few months. So I am quite aware of what they are going to use and what are the problems they are facing right now. So this data represents the motor level. So here I can see for first figure where these are the Indian drive cycle and what are the power requirement. So here at the y-axis this represents the vehicle speed, and this is the motor speed. It is represented in this graph, and over the time one sample result I have shown. So this data I have collected from Mahindra and Mahindra, and for this data, the induction motor that is used for 30 kilowatt induction motor, and these are the different parameter of induction motor. Now this second graph, if I the right side graph, it shows the power requirement for motor and for different operating conditions. So corresponding to the left hand graph, these are the power requirement and different time. So here we can see the power at kilowatt level. So maximum power it's required for particular some accelerating during accelerating is maximum power demand is 15 kilowatt, though motor rating is 30 kilowatt. So uh, power requirement mm, uh, at maximum cases is never exceed 15 kilowatt. That means if you calculate in per unit value, then it is basically half of the rating. Whatever induction motor they are using, so its maximum if it is a 30 kilowatt, so in practical cases they use for up to 15 kilowatt. So other 15 kilowatt they have planned for safety purpose, safety and precaution purpose. So sometimes there may be some critical cases like overloading, or some cases, some critical case may happen. So for safety purpose they keep some margin. So that is extra 15 kilowatt. So efficiency we have shown for that particular machine, it varies from 30% to 70% in different operating conditions. And next, coming to the next slide here, we can see that if we look at the graph at what's present in the left hand side, rated load versus efficiency plot. So here we can see when rated load is about 20 to 25%, that at that cases the efficiency is very poor. So, and in right hand side graph, that is plotted rated speed versus efficiency. So when machine operated at low speed, then also efficiency is poor. So here low speed means I'm talking about the speed is 2.5. That means 25% of rated speed, and light load or low load means it is 25% of rated load. So these are the things we can observe from the data. So all this data practically analyzed from Mahindra Mahindra. EVs. They have provided these graphs. So, induction motor, if we operated at rated condition, so it will provide approx 80 to 85% efficiency. So that is at maximum we can get 80 to 85% for well-designed induction motor, and this efficiency will decrease when it's operated at derated condition or light load conditions. So that time power factor also very poor, that is approx zero point 0.1 to zero point 0.4 in this range. And to cater these losses, so that time there is a huge losses in induction motor. So so significant of battery energy is drainage to cater the machine losses. So basically, this loss means the core loss. Uh, no load operation, during the no load operation of induction motor, the most of the losses were basically focused on the core losses. So core loss is huge that time. So this can be represented by these two graphs. Okay, so in electric vehicle application, what are required, that is motor with ample amount of overload capacity for safety margins, and sometimes this motor or electric vehicles may run at very low speed and light load condition. So these two requirements should be fulfilled at the time. So I have shown something in this presentation, so you can understand what is the need of the efficiency improvement of induction motor driven EVs. So this is the basic scheme for any drive system which is present in electric vehicles. So this is induction motor driven EVs drive system for. So there is a battery pack, then there is a converter, and converter fed the induction motors, and there is a load. So load may be in EV, that is passenger. We can consider the load. So we need to sense the current, voltage, speed to control this converter. And here is a input command. Input command is maybe the speed, maybe the torque. Torque may be the input command. So for such cases, let's say about the efficiency of a converter. The converter efficiency is about 95% to 98%. But let's say the machine is now operated at rated loads, then we can have the efficiency of induction motor is about 80 to 85%, and motor as well operate at rated speed. Then overall efficiency of whole drive system, we can observe that about 70 to 75%. This is pretty good overall efficiency of the drive system. But in the next scenario, now motor is operated at 20% load, and speed also reduces, and speed is now 25% of rated speed, and that condition efficiency of induction motor is 30 to 35%, and at this condition overall efficiency is about 25% to 28%. So this is very low speed, low overall efficiency what we achieve. So at low speed and low operating power conditions. So, so what we can see in that induction motor is only component which is primarily responsible for poor efficiency of the overall drive system when it's operated at light load conditions. So this hard reality needs or demand the efficiency improvement of such drive, which is used for electric vehicle applications. And these things is basically motivates us that if we improve the efficiency by very less level or very minor level, then it will lead a significant impact on the global energy. Okay, so that is the thing. If we improve the efficiency by 1%, that is enough uh, for these cases. So this is the basic focal point of today's discussions. So strategy, what I am going to adopt to improve the efficiency of a induction motor is coal loss minimization. By minimizing the coal loss, particularly at light load condition, by selecting the optimum flux of a induction motor. So, so what we can say from here, that is, so average full load efficiency of a well-designed induction motor is 80 to 85%, and this degrades further when it's operated at light load condition. In fact, motor are subject to operated at light load condition majority of its service life. So uh, besides, induction motor are also adapted in electric vehicles and hybrid electric vehicles nowadays. So, however, there are several advantages of induction motor, but moderate efficiency of induction motor puts a serious challenge for adaptation in EV and HEV applications over permanent magnet motor. In fact, battery use to cater losses become significant for induction motor drive. So this hard reality basically demands the efficient operation of induction motor drive, and this is the focal point of the whole presentation. So therefore, I will primarily develop an efficiency optimization strategy for induction motor drive, which will offer it, high efficiency at light load conditions. So this is the concept for implementation, how will improve the efficiency of induction motor drive. So figure which is shows in the left hand side, okay, it is demonstrates the different loss profile of induction motor with varying flux at constant speed and load torque. So the speed and load torque is constant, and here we assume the load torque and speed are not rated value, it's less than rated, we can assume that 20% of its rated value. So at such condition, if we see that induction motor core loss are this is core loss is subsequently reduces um, with the reduction of operating flux. So initially, this at this condition for this curve, this is motor is operated at rated flux. So at the time, this is the total losses. This curve is represent the efficiency. So efficiency is that much, and coal loss is significant amount of coal loss is occurring in the motor, and this represent the converter loss and copper losses. So as we reduce the optimum flux, so in this way we can reduce. This is this direction. I am reducing the flux, rated flux or machine flux. Then we can observe that coal loss is significantly reduces. Although the copper loss and converter loss will increase. So at some point at here we can see that where the coal loss and converter loss are minimum, at such condition the efficiency is maximum and overall losses is minimum at this point. So, so to get the maximum efficiency, drive should operate at optimum flux corresponding to a particular load or particular loading condition. So here, if we reduce this flux, and I observe that at particular flux at this condition, the overall losses are reduces, and that means total losses of the machines gets reduced, and that time efficiency is improved and efficiency is that time maximum. So particular cases. Now if I further reduces the coal loss by reducing the flux, this flux if I further reduces, then we can observe that total loss again increase and efficiency get decreases. So we need to come at a particular point where the efficiency is maximum. So that corresponds to the optimum flux point. So we need to achieve the optimum flux point so that we can get the maximum efficiency from the drive. And the right side of the curve is basically represents the torque versus efficiency and fluxes. So this is the rated flux conditions. What are the efficiency? Okay, so at the rated flux condition, this is the efficiency. As we know, as the load is increased, that means towards the rated. At here the this is the rated condition, the efficiency is very high, and at low load condition or derated conditions the efficiency is very low. So if I program my machine, or say the flux in such a way that we can program the flux, and the machine is now operated at optimum flux condition, wherever the machine operated at different loading conditions. So at different loading condition, this dotted green color curve it shows the program flux. That means when machine is operated at the optimum flux condition, so we can achieve some improved efficiency. So this is the significance of using the efficiency optimization, or efficiency or energy efficiency algorithm for improving the efficiency of induction motor drive. So that we can observe here from this curve. So at optimum points, optimum flux point, we can see that the efficiency is significantly improved. And this is basically shows the uh, flux different flux at different conditions. As torque is increased, so the flux, how flux is varies with respect to time. So this is the rated flux when rated load is applied. So now these are the background of efficiency optimization strategy. Now uh, at different efficiency optimization strategies can be found in literature, and these can be categorized as offline strategy and online or real-time strategy. And this real-time strategy again further classified as LMC, that is loss model control, SC, that is search control, and another is high bit control. So hybrid control is basically combination of these two, loss model control and search control. Both the strategies are combined and make a hybrid technology. So that is the hybrid technology. So here, so this is the loss model control at the right hand side at the top figure. So this is the general scheme of a loss model control technique. So what is loss model control? Loss model control estimate the machine losses by machine using machine model, and it set a optimum flux level by reducing the machine losses. And this technique LMC, that is loss model control, this technique is dependent on the machine parameter, because to calculate the machine loss, it use machine parameter like stator resistance, rotor resistance, inductance, and other parameters, speed as well. So we know that when machine is operated for a long time, the parameter is changes as the temperature is increases inside the motor. So once the temperature increases, then the parameter, that is motor inductance, resistance, will change. Okay, so it is very difficult to generalize a loss model with a constant parameters. So once the parameter will vary, so this loss model, whatever loss is estimated, that value is not accurate. So basically, this is has a accuracy problem, and this technique offers very faster convergence rate. However, the accuracy is dependent on the machine parameter. Another scheme that is basically uh, search control scheme. So search control scheme is in this scheme, optimum flux is obtained by iterative search method of the control variable by maintaining its output power constant. So this scheme is offer pretty good accuracy, and this scheme does not depends on the machine parameter. So that is the advantage of this scheme. However, it's require time to converge, and the figure which is shown here, that is right hand side bottom figure, that figure is shows a typical structure of induction motor drive operating under efficiency optimum conditions. And induction motor is operated in efficiency optimization control, and this induction motor fed by a two level voltage source inverter, and the algorithm is developed in a digital control board. So this is we are going to see how we'll implement the efficiency optimization strategy to improve the efficiency of the drive system. So these are different articles what I have observed past few years. So these articles that is used for loss model scheme, and later these articles are used in search control scheme, and we can observe these are the improvement at efficiency, and how the machine this but each scheme reduces the losses of machines and improve the efficiency of the machines. So loss model control, from this table we can see the convergence time is pretty low compared to the search control scheme. And these are the machine rating, though this scheme is parameter dependent, so parameter sensitivity is very high, but in case of search control scheme there is no parameter dependent. And last two scheme I have shown, that is hybrid control scheme. So its parameter sensitivity is medium. However, convergence rate is faster compared to search control scheme. But practical implementation of hybrid scheme is very difficult. So these are some literature from that we can have some information about the convergence time, whether the scheme is parameter sensitive or not, and how much efficiency has improved. So this result I got from studying this literature. So, what are the scope and challenges for the implementation of efficiency optimization scheme? So, these are a few issues that is based on the literature survey. The different issues we have found that efficiency EOS means efficiency optimization strategy. So, this strategy is quite complex for implementation. So this is the technique I implemented induction motor drive to improve the efficiency of induction motor drive. So here I have used a modified adapter quadratic interpolation technique. This is a mathematical tools so to improve the efficiency. So here the quadratic interpolation is very useful and efficient method for solving the optimization problem. So here in this figure, we can see we need to minimize this curve. So this is basically capital P IDS. This is the loss curve, and I need to minimize and we try to find out what is the minimum point of this curve. So we translate this problem in quadratic interpolation technique, that is with the help of second degree polynomial. So let's say this is the parabola. So we can approximate the quadratic function uh, to get this parabola. So instead of this particular curve, I want to minimize this particular curve, that is small p IDS. If I minimize this particular, if I try to find out what are the minimum point of this particular curve, and this, say, let's say this is the minimum point of this curve, say let's say this is IDSM, this is the minimum point, and let's say the minimum point of this farm curve is IDS star, and both these 2 points if very close, then we can say okay, we reach the minimum point. So if we approximate with quadratic function, as quadratic function is very easy to handle, so actually we will go for minimum value of quadratic function, and we will say that is the approximate solution of that particular problem. So that is the idea of quadratic interpolation technique. And so we, instead of this capital PIDS, we will going to minimize this curve. Okay, instead of this curve, we will going to minimize this curve. And if this IDS star and IDS M are very close, and then we can say we achieve the optimum point. So here the polynomial I can represent in this format. Okay, in this form. So this is small p IDS. This is second degree polynomial and parabola equations. So to get the minimum point of this curve, we just derivative with first derivative should be 0. So to get a lowest point or minimum of this curve, so first derivative is 0. So we have this equation number 3. So here we have these are basically the Newton divided difference. So from here we can have the minimum point. And if we have the second derivative of this equation 1, then we can fulfill the sufficient condition. So for the necessary condition for minimization, to get the minimization or lowest point of this curve, this will give the necessary condition, and double derivative will give the sufficient conditions. So now I will show the flowchart, how we'll implement these things in real time. So initially we have the three sets of data, that is IDS 0, IDS 1 and IDS 2. So what is this IDS 0, 1 and 2? So these are the flux corresponding current. So IDS is flux corresponding stator current. That is basically IDS. So we have initially we set 3 points. So IDS 0, I said 0. IDS 2 is the maximum value of stator component of current, that for a particular machine is 3.8. So whatever machine I have used, that depending upon the machine current rating, I will going to decide what will the maximum rating of that machine. So this is machine dependent. So in for particular machine what I have used, I found that IDS 2, that is maximum value of the flux component of current, is 3.8 ampere, and IDS 1 I have just get an average of these two. So we have initial 3 points: IDS 0, IDS 1, and IDS 2, and I take a tolerance limit, that is epsilon is 0.05. If the if I go the previous slide, if the IDS M and IDS star lies in this tolerance limit or tolerance band, that is 0.05, then we can say then we reach the optimum value. So we will compute first the IDS M using the equation what I have shown in the previous slide. So from these equations we can uh, compute the value of IDS M. So minimum value of that, and we will also measure the input power of the machine. That means what is the input power for that particular flux condition, and what is the input power and the rated condition or previous cases. So initially machine was operated at rated condition, so that is now represented by IDS1, um, or what is the minimum flux, uh, what is the power at the minimum flux condition, that is represented by this PIDSM. So basically we will measure power at different instance, and we will compare these two power here, and we will check whether the power is going in lower direction or towards the upper direction. So if power is reduces, that means towards the minimization direction, then okay, it's fine. If power is increasing in upward directions, then we need to again compute the flux value. So we will start like that, and we will check whether these differences lie within the tolerance limit or not, and we check whether the sufficient condition fulfill or not. If it is if it's fulfilled, the that means second derivative of that particular curve, polynomial curve, is greater than 0, that means positive, then okay, we can stop the iteration. If it will not fulfill, then again we move for the iteration. So here we'll come here. So initially, let's say IDS M is less than IDS 1. Okay, that means my minimum value of flux current is less than the previous instant of flux current. Now again we will check the power, whether this condition is fulfilled or not. If it is fulfilled, then the value of IDS 0, IDS 1 and 2 will modify. If it is not fulfilled, then again it will modify it as like in this way, and again it will come here, and again the iteration process will go on. So I will take one example. So let's say this is a particular case where the IDS 0 in this side, that is minimum value, IDS 2 is here, IDS 1 is here, and IDS M is here. So here we can observe a particular case. That means I have considered these two cases where the value of flux value, that is IDM, is less than IDS, and the corresponding functional value, that is PID, is also less than PIDS 1. So in this case, this is also true. From the curve, it can be observed these two condition is fulfilled. So that means this curve is looks like something like that. So we will eliminate this part. Okay, from IDS 1 to IDS 1 to IDS 2, this part of the curve will eliminate, and we will focus from IDS 0 to IDS 1 in this particular in this area. Because in this area minimum value will lie, and we will modify this value IDS 0, IDS 1 and IDS 2 like with this informations. We will modify this value and we will further continue these iterations unless until it will fulfill these conditions. So basically, what's happened in the line search technique, the initial interval is given and we will running the adaptive quadratic interpolation, and each iteration the interval size will reduce. That means we will eliminate a portion of curve or portion of the interval in each iterations, and the optimum step of interval should be very small, so that it is accepted to us and we can say, oh, we get the minimum value. So this is the whole thing. That is these things is developed in MATLAB, and I have implemented in induction motor drive, and I will show the scheme of induction motor drive here. So this is the whole scheme, that is field-oriented control scheme of induction motor drive with efficiency optimization strategy for EV application, electric vehicle applications. So here a typical indirect field-oriented control of induction motor drive used in EV is shown in this block diagram form. The squirrel cage induction motor is fed by a voltage source inverter, that is VSI, and the control scheme is developed in synchronously rotating reference frame and with two current sensors which are used here, that is this IA and IB. These two current sensors are used to sense the line currents. The efficiency optimization strategy, this strategy is implemented in the flux loop of the field-oriented control structure, and it will decides the value of flux component of current. Okay, and we will use this optimum flux component of current for further process of the scheme. So basically this efficiency optimization strategy integrated in the flux loop to decide the optimum value of flux component of current based on the input power requirement. So we can measure the input power from this converter input, that is what is the voltage at the converter, that is VDC, and current, that is IDC. So whatever the input of this converter, we can measure this and we can get the input power of the converter, and that I am going to use for implementation of this efficiency optimization strategy. And here another feedback is coming, that is omega r, that is the difference, speed difference of reference speed and the feedback speed. So this del omega r is the speed difference that also need one feedback, this efficiency optimization strategy, and this is required for let's say there is a speed change in the induction motor. Okay, in the machine there is a speed change. So when there is a speed change and speed change is this difference is very large, then efficiency optimization strategy will decides only sets to its rated flux. That particular transient moment, the machine will operate it at rated flux conditions. Once machine goes in steady state, then efficiency optimization strategy is automatically applied to machine. That is the thing. So that's why we need this speed information. So let's say for these cases, if speed between the speed, when the speed difference is lies within 1 radian per second, then we can say the machine is in steady state. Now we can apply the efficiency optimization strategy, and this strategy will automatically apply. we need not to worry about to application of this scheme. It is an automatic application process. So in this way, this will continue, and it will search for the minimum input power requirement corresponding to the optimum flux. And when it is the optimum value of the flux, that time the machine input will be minimum, and that gives the minimum losses of the machine, and hence efficiency of the machine will improve. And that particular cases we can say efficiency is maximum. So this is the thing, and here we can see a encoder is used for speed measurement purpose, and this actually closed loop operation of induction motor drive. And this scheme is developed in MATLAB Simulink, and later it is implemented in hardware as well. So here I can the machine parameter. What are the machine parameter and controller parameter that we have used in this scheme? So here induction motor that we use, that is 2.2 kilowatt induction motor. Its rated torque is 14 Newton meter. These are the voltage rating and frequency level. Number of poles is 4, and these are the other parameter in the that is magnetizing inductance, stator and rotor inductance, stator rotor resistances, and rotor inertia, and all these things. And these are the controller parameter, that is basically PI controller, what I have used for these cases in implemented this field oriented control. So this PI control value are shown over here. So KPS is speed control, and C means represent the current integral control. So these are the things that are these are symbolically represented over here. So now we'll focus on some results. These results are obtained from MATLAB simulations, and let's say a drive is operated at particular cases, say particular conditions. And I have already mentioned that the induction motors efficiency is poor when it's operated at light load conditions, right? So here all the results are going to present or taken at light load conditions, and we'll see how much efficiency is improved in these cases. So in this regard, a sample result over present over here. So here the speed is 30 radian per second. I have considered, okay, and the load torque is considered is 2 Newton meter. So this is mentioned here. The load torque is 2 Newton meter. That is 14% of the rated load of these machines. Here, figure A shows that speed tracking performance. So here, this is the reference speed. The black color and red is basically the feedback speed, or that we measure from the encoder. So it's demonstrate this basically figure A demonstrate the performance or speed taking performance of the machine, or when it's operated at rated flux conditions, and when it's during operation of optimized flux conditions. So let's say for first 5 seconds is it's operated at rated flux condition, and at 5 seconds I have enforced the efficiency optimization strategy at this point at 5 seconds. So later 5 seconds is shows the machine operated at optimized flux conditions. So what are uh, mm, the flux, or what would be the rotor flux, or with the stator flux, stator current, and input power. These are shown in other curves through the B, C, and D curves. So figure A, it is clear, quite clear that the speed tracking performance is quite nice and smooth. Throughout the operations. And figure B shows the flux component of stator current. So initially during rated operation is flux value is 3.8. When efficiency optimization is enabled, then flux component of current is gets reduced and it settle a optimized value, and it shows the corresponding rotor flux and input power as well. So this figure C demonstrate the rotor flux. So here rotor flux is orientation is perfect and throughout the operations. So as the stator component of current is reduced, so flux also gets reduced. So once the flux gets reduced, the machine input power gets reduced. So this was the input power before uh, optimization algorithm is activated. And once the optimization algorithm is activated at 5 seconds, the flux is gets reduced. The flux gets reduced, therefore the input power also gets reduced and settle a low value. So here we can achieve the input power reduction about 19.4% and efficiency is improved by 24%. So this is one result, and for a constant speed of operation of induction motor drive, which is which is used in EV, and these are basically flux reduces and corresponding input power is reduces, so like that. And second simulation result I going to show, that is vehicle drive cycle. This is one modified Indian vehicle drive cycle. So figure A shows the speed tracking performance and figure B shows the input power, corresponding input power. So initially, we run this induction motor at rated power conditions and rated flux conditions. So we observe the efficiency, what is the efficiency, what is the power. Now this motor is run again run at for a light load torque conditions, that is about 14% of its rated load, that is 2 Newton meter for this case. And we will study at rated flux condition what are the power requirement. So here this black color, black profile is represent the rated flux operations, and this is the vehicle's speed in terms of kilometer per hour, and it is operated at low speed, and that time power requirement of the machine also low. So this is the power requirement is shown by this black profile, and again this machine operated under optimized flux conditions. So once this machine operated at optimized flux conditions, then the power requirement is gets reduced. So the rate profile shows the power requirement at that time. So here we can observe from this analysis or from the data that efficiency saving is that much. That means energy saving is 17% for say 45 seconds of durations. We have a energy savings of 17%, and this is PT good saving for only 45 seconds. Now, I have tried to implement all these things in hardware setup as well. Okay, for validation of the scheme. So whatever we have studied in MATLAB now, I implemented in real time basis. So here a brief discussion of the hardware setup that we have developed in laboratory, that is shown here. So this setup is developed in laboratory, and the this setup is consist of two-level voltage source inverter, a DS1103 controller, that is digital controller, and 2.2 kilowatt induction motor with eddy current brake load is shown. So, so figure A basically shows the schematic diagram, and figure B shows the physical arrangement of the laboratory prototype. And uh, the major one of the major component of the setup is voltage source inverter. This voltage source inverter has power circuit card. There are gate driver card, signal conditioning card. There is a current sensor, voltage sensor. All are inside the this two level voltage source inverter in this module. And this module is designed and fabricated in laboratory specially for the validation of this work. And uh, we have emphasized on the cost effectiveness. So all whatever I will show different parts of this voltage source inverter one by one in the later slides. All the PCBs are designed with the help of Proteus software, that is Proteus 8.9, and PCBs are manufactured by JLC PCB, which is a Chinese company. And we just upload all the Gerber file, and they manufacture it and they send it to us. So the total PCB cost is around 200 US dollar. And all the component I have fabricated in labs. So, so this is the power circuit of voltage source inverter. Here, a dual half bridge IGBT module is used, and to use the to construct the power circuits. Okay, for such module are used one, two, three, four, and one module is used for brake chopper for these cases. And three legs are used for the inverter, and one is used for breaking chopper. So these are the power circuit configuration. This is the physical view. These are the gate driver cards, and which are basically uh, Skyper 32 that we bought these driver circuits, and we have designed the gate emitter protection card in laboratory. And this is the signal conditioning card. So primary function of this signal conditioning card is to amplification of pulse and pulse shaping. Okay, so the input pulse is coming from your the DS1103, that is digital controller board, and it's fed to the gate driver circuit of the inverter. So this card also designed in laboratory. So here in this card, we have facilitated with the date time. We incorporated different protections in this card. We have the fault detection scheme in this card as well. And if there is any fault in the inverter, so automatically it will shut down the inverter, okay, by stopping the input pulse. So all these things are developed in the laboratories. So this voltage and current sensor card also fabricated in laboratory. So here the current sensor card that is used LA55P, and voltage sensor card here voltage sensor that is used in LB25P. So here current range is up to 50 ampere, and voltage range we can measure up to 1000 volt. So these are the range of these cards. And this card is used for measuring the current. Sensor card is measuring phase current of each phases of inverter output, that is motor input current, and as well as for DC link current. Similarly, the voltage sensor card used to measure the pole voltages as well as the DC link voltages of the machine, of the inverter. So, with the help of the setup, we have some experimental result as well. We have tested the machine at the similar condition what I have shown in simulation. So to study the effect of simulation result, whether the scheme is perform well, or whether there is any noise or any issues, that we have tested. So that's why we tested in the similar environment and same condition, same speed pattern, same load torque condition. So here machine is operated with a constant steady speed of 30 radian per second, and load torque was 2 Newton meter, that is 14% of the rated load. And from figure A, it can be observed the speed taking performance is quite good before of enabling the efficiency optimization strategy and after enabling the efficiency optimization strategy. There is no change in speed response. So speed response is quite, speed taking performance is quite good. And once the efficiency optimization is enabled at 5 seconds, the stator current is gets reduced and corresponding rotor flux and input power gets reduced. So here the efficiency is improved by 14% and input power is reduced by 18.9%. That we can achieve at that particular cases. Now, this is another experimental result to demonstrate the drive cycle of machine. Actually, that drive cycle test is validation is quite difficult. So I have applied some other speed pattern, that is trapezoidal speed pattern. So here we can observe for first 20 seconds the machine operated at rated flux conditions, and first 20 seconds and later 20 seconds the machine operated at efficiency optimization strategies. So if we look the speed response, so the reference speed and actual speed, that is motor speed, which we can got from the motor encoders. Okay, so both the speed is matching and speed response is fine. So before enabling the optimization algorithm and after enforcing the optimization algorithm, there is no change in the speed pattern. But we can observe the input power gets reduced when we enable or enforce the optimization strategy. So after 20 seconds, we enable the optimization strategy, where we can see that there is a uh, uh, reduction of input power, and this power is reduced from 2026 joule to 1469 joules. So there is an energy savings of 557 joules, and percentage, if you calculate in percentage, so that is 27%. So this is quite a significant improvement we have achieved. So this is the motor gear ratio and the motor rating, wheel diameter, and this is vehicle speed as shown in here. So again, we have tested this machine at different operating condition, different speed pattern, different loading condition, and few results I have shown in this table. So when machine rated rotate at particular speed, say 20 radian, that is 191 rpm, and different speed when torque is 0 and torque is say 1 newton meter and 2 newton meter. So this is the input power requirement when it's operated at rated flux, and when it's operated at optimized flux condition. So input power is represented, that value, that in watts. So there is a significant reduction of input power when used in optimized flux condition. So this is if we talking about the percentage value, then it's is 39.6%. So efficiency at the time can calculate because output power is 0, and when machine is operated at 1 newton meter, that means 7% of rated load. Then efficiency improvement is 55% almost, that is 54.5%. And when machine is operated at 14% of the rated load, that is 2 newton meter, then it's 26.1%. So as speed is increased, and as the load is increased, so this amount of efficiency improvement is achieved. So at low speed, 40 radian is okay. This is, we can consider as a low speed, and at that point we can achieve 19.8, almost 20% of efficiency improvement. So these all these data are real time data. That means we observe from hardware setup. And again, this is basically uh, uh, whatever data we have observed that are again plotted in graphical manner, so for better visualization purpose. So figure A shows the input power and its corresponding uh, uh, the rated what are the input power at for rated flux condition is shows in this color. Okay, and the orange color basically shows the optimized flux condition, what is the input power. So at different speed pattern, different loading condition, this is the input power requirement for rated flux and corresponding cases. That means same power loading condition, same speeds. This is the optimize flux conditions, the input power requirement. So here this is the optimized flux condition. So from this figure, it is observed that when machine is operated in optimized flux condition, input power is significantly reduced. So this can be observed at different speed and different loading condition. Similarly, figure B is shows for the in percentage improvement in terms of efficiency and input power reduction. So 1 Newton meter at 20 radian per second, efficiency improvement is about that much, and input power reduction at that much. So it shows and different loading condition, different speed pattern is shown. So these are the characteristics we can observe from the machines. So basically, what I am telling that from this curve, that if we enable this efficiency optimization strategy, and if we implement such strategy in induction motor drive, which is used for EV applications, then there would be a significant amount of energy savings. And once we save some energy, that means we can drive that vehicle for some long ranges. So this efficiency optimization strategies basically does it will improve the driving range of electric vehicles. That is the significance of this work and this of this present work and efficiency optimization strategies, what we call. So again, here in table format, some data is present. So at rated condition, that means rated flux conditions, this is the electrical energy consumption and mechanical output is that much. So efficiency at that particular cases, when machine is operated at such or provide such output, then efficiency is 67%. And when we enable the optimization strategy, then electrical energy gets reduced, and mechanical still it will deliver same amount of mechanical power, and efficiency is improved by some percentage. Now its efficiency is 77.4%. That are the analysis from the data what we have observed from the results. So here I have shown some comparative analysis. What are the available methods? What are the available methods in the literature, and what I have implemented or what I have proposed. So there is a comparison of different methods. So these are basically P and O part of an observed method. P and O means part of an observed method. So with the help of this method, which is implemented in some literature, so this 13, 14, 15 are basically the literature number, that is reference number. I'll show this now, these references at the end of the slides. So using this particular method, we have seen the improvement of 12%, and its conversion time is about 5 minutes. So it is very and it takes very long time to converge, and the motor rating is 10 HP. So, although these methods implemented in for other literature 14, 15, so here improvement is 12%, and here the convergence time is not specified at particular cases, and here we can observe the 7 second. So, 7 second is pretty long time to converge a particular algorithm. So in case of electric vehicles, where the dynamic speed is dynamically changed, load is dynamically changed. So that cases 7 second is pretty long time. So, this type of method we can apply in EVs. Okay, so though this method can be applicable in industry where the drive is operated at particular load for longer times. There is a significance of this method in case of industry, but if we're talking about the electric vehicles, then this method is not applicable, is not significant at all. And again, the other method that's proposed in other papers, that is GS, its full form is golden section method. This is very quite interesting method. This is also line search technique. So here the improvement is about efficiency improvement is about is 39%, and is convergence time also drastically reduced from 7 second to 2 second almost. That is this is very good one of the good method, and there are other method, fuzzy logic based method, ramp method. These are convergence time of 2 seconds like that. So my objective, one of the objective is to minimize the losses and improve the efficiency of machines, as well as the improve the convergence times. So what I have observed that in what we have implemented, that quadratic interpolation method, its convergence time is around, maximum convergence time is around 1 second, 0.8 to 1 second, and other cases it may be less than that. So we consider this method is faster compared to other method what are available in literature right now, and this is the efficiency improvement is 20 to 26% almost, and input power reduction about this percent. All these methods are basically search control method, and that's why this method does not require machine parameter, so it is parameter insensitive methods. So these can be implemented in vehicles, and this method gives quite accurate results for finding out the optimum value of flux. Now, coming to the conclusion part, so what we have observed that average efficiency improvement at light load condition is about 20 to 26%. And so that is the achievement, I can say. And this efficiency optimization is employed in the flux loop to get the optimum flux. Therefore, we need not to modify the hardware setup or um, any extra hardware requirement. Is there is no requirement of any hardware circuitry. So we just simply modify the control algorithm. So that is can be easily implemented in industry or electric vehicles. And this control algorithm is very simple. This is very mathematical, mathematics oriented, and implementation is quite easy. That is the thing, and the flux, this optimum flux. Basically, we want to achieve the optimum flux where the machine losses is reduced. Basically, the code losses is minimized or reduced, and consequently, the input power consumption is gets reduced, and efficiency, overall efficiency is improved on the entire system. So, and yeah, the convergence rate of this algorithm is 0.8 to 1 second. This is quite fast compared to other methods uh, which are available in the literature. So these are the things that we can implement in vehicles, electric vehicles, to improve its driving range. Where the induction motor, especially induction motor driven electric vehicles. So coming to the next slide, these are the key references that I have mentioned or I have used for literature survey, and these are the publications from this work. These are the journal publications. These are the conference publications related to this work. And thank you for the time and patience. Now the session is open for the discussions. Ma'am, you are not audible.
Am I audible now?
Yes, ma'am. Yes.
Okay. I said, Abhishek Paul, you have explained it so well that a student like me who has never studied science and I never liked science understood what you said. So thumbs up for you.
Thank you.
Your topic was quite difficult: energy efficient control scheme of induction motor driven electrical vehicle. Very long topic, but you did justice to it and you've done it very well. Thank you very much, and keep it up,
Thank you.
keep
Thank you, ma'am.
going, and we really enjoyed it. Thank you once again. Now, coming to first to begin with the mantra of IGP, feed your skills. We invite the second speaker. I have no information about them, but they will introduce her with a short video. So let's see that about the second speaker. Abhishek, is somebody there?
No, no, no.
No one's there, but I'm really pleased with you. Although I like the remarks given by one of the participants, Manilita Ramas, that yeah, it's good that these days don't need to have cars. We can do without cars. They pollute the environment.
Yes,
But do you think these cars would help in controlling some or bringing in some climate change?
yes, yes, definitely. It will help in.
Do they produce carbon dioxide?
No, no, no. EVs not produce any carbon dioxide or any gases. If
Monoxide? Huh. Yes, because then we already have too many cars. Now the flying cars are coming. Aren't you working on those? You're not working on flying cars?
no, no, no. I'm
Like,
not working flying.
no? Okay. But very nice, very good. And I would like the organizers to tell about the second speaker. or the video. This was 349 webinar today. Oh my God, so many. And I would like to quote some of the people here. And he said, Ratan Tata, you heard his name being in India?
Yes, yes.
Ratan Tata, yes. He said, I don't believe in taking right decisions. I take decisions and then make them right. So always believe in your ability and your efforts. Tell yourself all the time that you can do it. And I'm sure you're going to leave your marks like others, um, like footprints on the sands of time. Lovely to have you here, but it was very long. I think you need water. You had 1.5 hour, more than 1.5 hour to speak continuously.
Thank you, Mansi.
Keep it up. I used to encourage my students like this. Where are the organizers? Umme Salma, are there I forgot to congratulate Jocelyn Julian Noga. She's going to get a special gift. IGP says that we've noticed that till now she's been attending most sessions with us. We'll share a lifetime membership certificate with you. Congratulations. It's very difficult, to take out time for these things, but the urge has to be there. Lives of great men all remind us we can make our lives again, and departing leave behind us footprints on the sands of time. Someone has rightly said, in order to succeed, we must first believe that we can. And another quotation is that never miss the first opportunity. We usually wait for the right time. That right time may not come. avail it because you will never miss the first opportunity. We can be destructive or creative if our energies are not released into creativity. They are bound to become poisonous and harmful. So always be positive in your life. That's my experience. Positive in thinking, positive attitude, positive outlook. Don't be afraid or disappointed if you fail because you are doomed if you don't try. Let me remind you again, don't forget to share, tag, comment, and mention your friends in the comment box because your attachment encourages us to do better and best service to our lovely audience. Our mission is to empower our youth, so stay with us by your support. Always. When you are greetings or you're sending your love or saying hello, please write the name of your country also. I've only seen one person from my country. I don't know about others. Getting how many think it's a boring subject or a very interesting subject? Zero questions. Okay. 5 out of 10. Leaderboard. Everything can be changed by facing the change, but nothing can be changed by changing the face. See how wise people have rightly said things. The secret of happiness is not in doing what one likes, but in liking what one does. How many of you really agree to it? No steam or gas drive or anything until it is confined. No Niagara Falls is ever turned into a light and power until it is tunneled. No life ever grows great until it is focused and disciplined. I haven't seen any questions. How did you select this subject, this topic that you have, energy efficient control scheme of induction motor driven electrical vehicle?
Yes, yes.
What made you select this topic?
Uh, Actually, I have an interest in this field, basically electric vehicles. So nowadays, electric vehicles is the alternative to the traditional vehicles. So I have some background in machine drive, so I choose this topic. And uh, country like India, Bangladesh, some this type of country, here rare earth material like direct magnet is not available. Uh, that is one foundation, and we need to purchase the permanent magnet from other countries, and the cost is very huge. So that's why I focus on such a machine where permanent magnet is not required. So that's why I have taken this area. How can I improve the efficiency of that particular machines so that it will contribute something in real life, in electric vehicles. Uh, that
These
is the
would be
thing.
cheaper. You think these would be
Uh,
cheaper?
this machine is cheaper, so overall cost of the electric vehicles gets reduced. And if I improve the efficiency, so that driving range also improve for electric vehicles. So that is the reason for choosing this topic.
Good. No, it was very interesting and informative.
Thank you.
People must have gained a lot of knowledge. I don't see any questions coming. That
Okay.
means everybody has understood or nobody has understood. Can we have one of these? Thank you, Raj Narayan. He says you created a benchmark in global professional community. I agree. I agree. 100%. So, have you worked on other projects too?
No, no, no. Currently, I'm not working on our project.
This is the first one?
This is first one, and in future I will work. That is my plan. It is in my plan, that is I will work for uh, charger to develop a infrastructure for charger or charging station for electric
Okay,
vehicles.
okay. Yeah, that's very important because otherwise it can't work.
Yes, yes.
So maybe one day you have your own station, electrical for electrical cars, charging station. Do you have labs for this?
Yes, yes. In Khapar, there is some lab for electric vehicles research.
Okay. No questions are coming. I don't see any. People must be satisfied. All remarks were very good because I was going through the remarks all along. Now they are more interested into the quiz competition winners. That shows that if they have understood, they can answer the quiz. Are you teaching at some university?
Yes, yes, yes. I'm
The same?
assistant professor at yes, support.
Chapter. Okay, good. I have also taught at different universities.
Okay.
Well, thank you very much again, and I really enjoyed your. Uh, Not being a science student, I enjoyed your presentation.
Thank you, ma'am. It's mean a lot.
It was a pleasure. It was a pleasure. Didn't get any cue? Thank you. The spelling of thank you. चला गया वो? What did he say?
वापस आओ तो हर जगह से ब्लॉक करेंगे
Hmm?
सबके फोन ब्लॉक करेंगे जिससे कॉल करो उसको बंद करके ब्लॉक कर लेते हैं आप अपना फोन यूज करिए
Dear participants, thank you very much for joining with us in IGP. Today, some of our technical problem we cannot share our today's webinar code. So just collect the certification link. We will provide this code tomorrow or later. Thank you very much.
Are we going to have the other two speakers?
No, ma'am. Today we have one speaker only.
Okay, thank you very much. And we are obliged to all our marvelous people who have attended this webinar and to the speaker for marvelous presentation and giving us your valuable time. This session will be effective for our audience because you shared your intelligible knowledge with us, and I agree to this also. Thanks for enlightening us with your pearls of wisdom and story. This is for Abhishek Pal. No doubt our viewers will be benefited today by the awareness that received through your technique. A very lovely presentation. Yes, it was. So with this we conclude, and I thank everybody who attended this, and I'm sure you must have gained some good knowledge. And my dear knowledge seekers, I would like to thank you all for attending this, and optimistically, hopefully, you learn something new and you will implement in your life. Please leave a review, recommend on our page. If you learn something or we help you a little bit, don't forget to collect your e-certificate. And today, because they have already told you that you can collect the certificate, they have not given the code number, which they will give tomorrow. With this, we conclude. Thank you very much. IGP, thank you very much for doing a great job. Stay happy and safe. Viewers, please spread the information to your friends and hope to see you again in the next webinar. Thank you so much to our guest speaker, Abhishek Paul, and pleasing viewers. It is always a pleasure. There were some very nice remarks. I was going through them. I liked them. And my worthy viewers, I would now request you all please leave a review of today's session. I've already requested you, and so also recommend in our page if you learned something from us and we were a little helpful to you all today, and also request to beautiful onlooker to spread the information to your friends and community. And do collect your e-certificates. And don't forget to join our new webinars, coming webinars. The three, it should be 350, 351. So you can join them. Thank you very much. Bye bye.